The H. Bolton Seed Medal is awarded for outstanding contributions to teaching, research, and practice in geotechnical engineering. And the 2008 Seed Memorial Lecturer is Dr. J. Michael Duncan, P.E., Distinguished Professor Emeritus at Virginia Tech. Our speaker tonight has provided a lifetime of distinguished contributions that match the examples set by the other distinguished recipients of this award. Professor Duncan, would you join me at the podium, please? Professor Duncan, in recognition of your many outstanding contributions to teaching, research, and practice in soil strength, slope stability, and dam and levee design, I take great pride in presenting you with this medallion and certificate. Thank you, sir.
Thank you very much.
Thank you. And also thank you, Dr. Duncan, for taking the time to prepare the lecture. We know it's quite an effort, and for coming to the conference tonight. We're all very happy to be here, and we're very glad you're here with us. Dr. Duncan was one of Professor Seed's first and certainly one of his most accomplished PhD students. Their long relationship as collaborators and colleagues certainly makes this recognition most appropriate. Professor Duncan received his bachelor's and master's degrees in civil engineering from Georgia Tech and his PhD from the University of California, Berkeley in 1965. At the completion of his studies, Dr. Duncan joined the faculty at Berkeley, where he became professor of civil engineering in 1973. And after 19 years at Berkeley, in 1984, he moved to Virginia Tech and served as the W. Thomas Rice Professor of Civil Engineering. Dr. Duncan now holds the title of University Distinguished Professor Emeritus at Virginia Tech. Teaching is one of the three criteria for the H. Bolton Seed Award, and Professor Duncan is recognized as a master of this skill. He's known for his lucidity, simplicity, and logic, both in his writing and his teaching. His enthusiasm and unending commitment have endeared him to his students, many of whom are here today. Dr. Duncan's longtime colleague, Professor Jim Mitchell, said of his friend, his ability to organize and develop technical topics, always relying on first principles and consistency, and breaking complex problems into manageable pieces, has served as a master template for students to develop their own skills as problem solvers. Professor Duncan has been recognized with 3 outstanding faculty awards from the University of California, Berkeley, and 4 College of Engineering Teaching Excellence Awards from Virginia Tech. In addition to his teaching honors, Professor Duncan has been honored for his tremendous contributions to the advancement of the profession. He was elected to the National Academy of Engineering in 1985, and he was elected as a distinguished member of ASCE in 1999. He's been the recipient of a number of prestigious national and international awards and medals, including the Terzaghi Award and the Outstanding Civilian Service Award by the Department of the Army for his service as the co-leader of the U.S. Army Corps of Engineers Interagency Performance Evaluation Task Force that investigated the performance of the levees and floodwalls here in New Orleans. Dr. Duncan has delivered many of the country's most prestigious professional lectures, including the Terzaghi Lecture. Professor Duncan has served on numerous boards of consultants in service to private and governmental organizations. His assignments have included many dam projects, as well as projects related to ports, landfills, and highways. He's a trusted advisor and a key consultant to the U.S. Army Corps of Engineers, who've called on his expertise in dam evaluations, in the development of engineering manuals, and in the development and presentation of focused short courses. Since 1986, he's also served on the Geotechnical Advisory Board of the Panama Canal. Professor Duncan has been involved in research, of course, throughout his long career in the areas of seepage and drainage, slope stability, strength and deformation properties of soil, and finite element analysis of earth masses. He's published over 200 papers and has developed manuals of practice on a variety of topics. Dr. Duncan has also been making our profession better for close to 5 decades. He served the profession and ASCE through his volunteer activities at the section level in San Francisco and his national activities, including chairing technical committees and chairing the ASCE Geotechnical Division, of course, which later became the Geo-Institute. His numerous awards, presented by both his peers as well as his former students, identifies his tremendous accomplishments as a teacher, advisor, and mentor. Dr. Duncan's original research in soil strength, slope stability, and dam and levee design form the foundation of the work being done in those areas today. His knowledge and insight have been recognized by his colleagues and peers around the world, and as his good friend Dr. Stephen Wright at the University of Texas wrote about Dr. Duncan, contributions to any one of these three areas of practice, research, or teaching would be sufficient for one to receive this award. Mike has distinguished himself in all three. I'm sure we all agree with Dr. Wright that Professor Duncan is extremely well qualified to present his lecture titled Failure of Flood Walls During Hurricane Katrina. Ladies and gentlemen, I present to you the 2008 H. Bolton Seed Lecturer, Dr. James Michael Duncan.
Thank you very much, Art. I am very grateful for this award and for the opportunity to give this lecture in honor of Harry Seed. Before I begin my lecture, I'd like to pay tribute to Harry Seed and acknowledge his contribution to my life. Harry went to Berkeley in 1950, and he was joined there in 1958 by Jim Mitchell. Together, Harry and Jim built a geotechnical engineering program that was incredibly successful. Over the 3 decades that Harry and Jim worked together, the program had about 1,200 master's and PhD graduates. I was fortunate to be one of them. Harry taught many of the classes I took at Berkeley, and he was my PhD supervisor. I was privileged to be able to join the faculty in 1965 and to work there with Harry until 1984. I had the pleasure of knowing him as his student in the classroom, as his teaching assistant, as his research assistant, as his faculty colleague, and through our work together on consulting projects. You will have no trouble understanding the great influence that he had on my life and my career. Einstein said that you don't really understand something until you can explain it to your grandmother. I think that kind of thought was what guided Harry's approach to his work. His lectures were like that, crystal clear. Your grandmother would have been able to understand. When you worked with Harry on a research or consulting project, he would do things over and over, or more often, he would have you do things over and over, until he found just the right way of plotting results of tests or results of analyses that made things crystal clear so that they needed virtually no explanation. Then he would write a crystal clear explanation, working just as carefully on the text as he had on the figures and tables. Those of us who were privileged to work with Harry learned just as much from watching him work as we had from his lectures and papers, and I'm sure that many of us emulate his methods as well as we can. He taught us all by his fine example, as well as by his lectures, papers, and reports. I can say without doubt that Harry Seed was the single greatest influence on my career, and I'll always be grateful for his instruction and his guidance. When she learned that I would be giving this lecture, Harry's daughter, Carol, sent me this photo of Harry and me in China in 1983. When Carol found I was going to give this lecture, she sent me this photo taken in 1983 when Harry and I visited China. I'm very pleased with this photo. I think it's probably the best picture ever taken of me, and I'm very happy that it's with Harry. No matter When or where? Harry was always teaching. Here he is instructing one of his younger students on the properties of gravel and cobbles. Here's a photo of Harry at one of the memorable moments in his life, two great men meeting. It's rumored that one of our Berkeley students who saw this photo said, "Who is that with Professor Seed?" Harry Seed was a uniquely capable engineer and a very special person. Watching him in action was like watching Michael Jordan play basketball or watching Brett Favre play football. What came through was not just his exceptional talent, but his enthusiasm and the fact that he had fun doing what he did. The enthusiasm and the fun were contagious, and I'll always be grateful for what he taught me, for the example he set for me, and for the time I was able to spend with him. Thank you very much for allowing me the opportunity to make this tribute to Harry Seed. I have one more thing that I would like to take just a minute to do before I get into the topic of my lecture. And that is, you may have noticed quite a few young men and women here in maroon shirts with VT on the front. These are Virginia Tech students who drove all night to get down here. I'd like to ask them to stand, please. And before you sit down, I would like to ask the Virginia Tech and Berkeley alumni in the audience to stand. Will you please? Okay. Well, the title of my talk is Failures of Flood Walls During Hurricane Katrina. Before I get into the technical aspects of the lecture, I have many people to thank because this was an effort, a team effort, and the team was large. First of all, Tom Brandon, my colleague at Virginia Tech. He and I worked many long hours together, often ending the day pretty late by my standards, and just at the point of deciding what needed to be done the next day. And when we got that far, more often than not, Tom would tell me, "Well, I think I can have that done by morning." Now, I'll tell you, there are no nicer words that a fellow worker can tell you, is that it'll be done by morning. Also, Steve Wright, University of Texas, he worked with us. I never feel fully confident of slope stability analyses until Steve has worked on them and said that they are correct. And Steve was just a great help in this effort. These folks here, Reed Mosier was my co-leader on the levee and flood wall investigation team. Noah Vroman also works at ERDEC, as does Ron Wall, George Sills. Joe Dunbar is the geologist who sorted out difficult geologic questions. Mike Sharp and Scott Stedman did centrifuge tests, and I'll show you the result of some of their work. And last, Jim Mitchell. Jim Mitchell was not on the IPET, but things had to be done in such a rush that we developed a system of having virtually real-time review. And Jim was the member of the external review panel for ASCE, who was concerned with the geotechnical issues. And it was such a pleasure. Jim made very many excellent suggestions, and he did it all so quickly in such cooperation that it didn't slow the effort down at all. So thanks to all of you who contributed so greatly to what I'm about to present. About 2/3 of the damage during Hurricane Katrina resulted from breaches in levees and flood walls. And I'll be talking about some of the breaches in flood walls. The breaches were important because where the protection fell down, more water poured through the breach. And so about 2/3 of the water and 2/3 of the damage was due to these breaches. The most concerning were the failures of walls that were not overtopped. So as the water rises here, before it gets to the top of the wall and we have an overtopping incident, possibly overtopping failure, with the water still below the top of the wall, the wall moves and fails and there's a breach. The IPET investigation enjoyed a great deal of resources provided by the Corps of Engineers. We had topography from as-built drawings. We had pre-Katrina LIDAR and ground surveys. We had soil conditions from pre-Katrina borings and from new borings and CPTU tests in adjacent areas that were still intact. And then we had 3 analysis teams, Tom and I at Virginia Tech, the folks at ERDEC, and Steve Wright at the University of Texas, all working to check each other, do quality control. Everybody did quality control on everybody else's work. This is a photograph, an air photo of an area just to the north of here. The Sheraton is here, about 5 miles up to the shore of Lake Pontchartrain. I'm going to be talking about the 17th Street Canal failure that was right here, and also the London Avenue, London South and London North failures on that canal. These yellow lines are eye walls, and the failures were in eye walls. The 17th Street Canal eye wall was 27,000 feet of flood wall. It was constructed in 1990. The levee rests on marsh and lacustrine clay. The borings are spaced at 500 feet apart. 17th Street Canal cross-section looks like this. The levee fill was placed on this marsh. Now, I learned in this investigation marsh is not peat, but it's something like peat. And it's very compressible, it's highly organic, and its high compressibility is what is responsible for the shape of this profile. This levee fill is sunk several feet into the marsh material. The levee has an unusual cross-section. It's lower on this side of the eye wall, and that's because when there's very little water in the canal, you have a stability problem toward the canal, and that's why the levee crest is lower here. Now, beneath the marsh, there's this lacustrine clay that turned out to be somewhat weaker than the marsh, and so a critical factor in the stability problems. Beneath that are beach sand, bay sound, estuarian clay, and so on. These deeper deposits don't come into the stability picture. This is a view of the 17th Street Canal breach. The eye wall you can see here has failed and been shoved inland by the water. And of course, there's a great deal of flooding, as I said, with essentially all of the flood protection removed at this breach. The marsh, here you get a very good view of the material. It is highly organic and has a lot of properties similar to peat, but it also has cypress stumps within it. The marsh is material that accumulated and sedimented in a cypress swamp. And so there are remnants of those cypress trees in the marsh. A key element in understanding the failure was the trench. This is a photograph of a trench that was excavated by Joe Dunbar, and it shows that we have here the marsh, we have the clay, and beneath the clay we have more marsh. Now that's not the way these materials were laid down or deposited. The marsh was deposited, the marsh formed on top of the clay. So how did it get in that position? Well, starting from something like this, during the failure, this eye wall and this soil in front of it moved inland, slid along a slip surface that would look something like this. So it started out in this position, and with that shearing movement, the chunk of clay was moved up in between two pieces of the marsh material, winding up in this position. And so this shows that the failure surface was down within the clay, and is only through the failure itself that we wind up with the marsh, clay, marsh sequence. Clearly then, the shear strength, the undrained shear strength of the clay was a key thing to understand about this failure. And one of the best pieces of data, it seemed to us, I say best because the scatter was much less for these piezocone tests than for laboratory tests on undisturbed samples. And within the interval of this cone profile, where the cone is penetrating the clay, there's very, very consistent data. And we used a method developed by Paul Main to determine the shear strength of this from the cone penetration results. And the slope of this line here is about 11 pounds per square foot increase in shear strength for every foot you go down. Now that's a very common number. I tell my classes that this number should always be between 8 and 12. And if it isn't, likely something is wrong. And so that fit right within that picture, and there are these little traces here that don't deviate very much, are from 4 different cone penetration tests. And we relied a lot on those cone penetration tests to tell us the shear strength of the clay. Here's a comparison of a line, the shear strength of that clay, that's 11 PSF per foot. Going down there, superimposed on the results of laboratory UU tests on specimens from beneath the crest of the levee. The rest of the strength profile, this is the part that's in the marsh, and this part here is in the levee. Lots of scatter, but clearly stronger. And then these are UU tests on specimens from beyond the toe, where the clay had been subjected to smaller consolidation pressures. And this line then, this is the strength within the marsh here, and this is the strength derived or predicted, suggested by the cone penetration tests. Perhaps a little lower than the UU test, but a consistent variation. And so putting those things together gave us what we call the IPET shear strength model. And the most important part of this is down in the clay, because the clay was the weak link. The clay increases with strength at 11 pounds per square foot per foot under the crest and also out beyond the toe. And the only difference is where it starts, and that's determined by the amount of overburden pressure, the pressure to which the clay was consolidated. Above that is the marsh, and beneath the crest of the levee, the marsh has been compressed very considerably due to the weight of the levee, and then this is the levee fill strength. Out beyond the toe, the marsh is thicker but weaker. We can compare those lines with the strength profile that was used in design, and that's shown here. So up in the levee, a lower strength than we estimate is the best guess. Here in the marsh, very similar strengths and a similar increase of strength with depth. And then at below minus 20 feet, the district used a constant strength. Not a great deal of difference. In fact, the strength used for design, this black line, shows somewhat lower strengths than we estimate with all the benefit of hindsight. And then out under the toe, beyond the toe of the levee, a considerably lower strength. Now this black line, this was used beneath the crest, beneath the slopes, and beneath the toe of the levee. So we think that this black line is too high an estimate for those areas, but it is just about right or a little bit conservative for beneath the crest. Now if we take those strengths and apply them, what we have for levee fill makes very little difference because the slip surface hardly touches the levee fill. The marsh strength is not very important because so little of this slip surface goes through the marsh. The important thing is the clay strength down here. If we do this kind of standard stability analysis, we come up with a factor of safety in the neighborhood of 1.3. But this leaves out what we believe is the most important aspect of the stability of these eye walls. And that is that as the eye walls deflected, a gap formed behind the eye walls. That gap was filled with water. The formation of the gap and filling it with water increased the load on the wall, and we had the wall loaded like this. Hydrostatic water pressure from the water level here to the bottom of the wall. And if you think about it, this is a higher pressure than the earth pressure. Otherwise, the gap would not have formed. It's the fact that the water pressure is higher than the earth pressure that causes the formation of this gap. So when the gap forms, we're loading the wall with a greater load than just earth pressure. And so the proper way to analyze that is to consider that with the gap behind the wall, there might as well be nothing but water over here. It doesn't matter how far it extends. It's water that loads the wall. And the slip surface stops at the bottom of the wall here. So this is a proper modeling of the failure mechanism. And this, combined with those strengths I've talked about, gives the factor of safety very close to 1. Now, confirmation of this mechanism was given by the centrifuge test that Mike Sharp and Scott Stidman performed. This is the large centrifuge at Erdek. This is a photograph taken from a film of a test in a smaller centrifuge and at RPI. And those of you who are RPI alumni will notice that I've turned this backward. It's not an insult, it's just that I want things to go in the right direction. And if you look at this photograph here, you can perhaps, you need me to tell you, the water level starts right here. And in a series of photographs, you'll see the water level rise, you'll see the wall start to move, and this soil out here begin to slide. And if we do that, one click at a time, see the water level coming up there, and you can see the wall beginning to move. At this point, there is a gap behind the wall. It's obscured a little bit by the fact that when that gap formed, a triangular chunk of soil calved off the rest of the clay back here and began to fall down and follow the wall. Let me go back through that sequence again, because I want you to notice this time, watch these markers down in here, and you can see that these markers near the top of the clay move as the markers within the peat, within the marsh. I began to call this the layer formerly known as peat. But so here we go, raising the water again. And you can see those markers at the top of the clay now begin to move the same as the marsh, like that. Now, those centrifuge tests were very useful in showing the same mechanism as we deduced from the stability analyses. And here in the field, in a number of places where the walls hadn't failed, there were these gaps that had formed but didn't lead to failure. So the main factors responsible for the 17th Street eye wall failure were, number one, the design strengths were too high beneath the slopes and beyond the toe of the levee. They were fine beneath the crest. And the design analyses did not include a gap between the wall and the levee fill on the back of the wall. Now let's move to London Avenue. London Avenue had two failures, south and north. The soil conditions are different there. There's sand beneath the marsh. And this is the breach. It's only about 60 feet wide as compared with about 400 feet wide at 17th Street. But a large amount of sand washed through this breach into the neighborhood. There were very high flow velocities that carried a lot of sand into the neighborhood. The soil conditions at London Avenue were that there was sand beneath the marsh layer. There was no clay in the profile at the London South breach, and there was a thin clay layer at the London North breach. The sand is dense at the south and loose at the north, and this has to do with the energy environment where the sand was deposited. Cross-section at the south looked like this. Notice that it's foreshortened here. This drain over at the Warrington Drive is further on over than it shows in this picture. And the canal water level at the time of failure was about in this neighborhood based on the eyewitness tests and so on. Possible modes of failure were, number one, erosion and piping due to high hydraulic gradients in the sand. Number two, instability caused by water loads and uplift water pressures in the sand. Now, when we form a gap in sand, the situation is slightly different because the gap can only go down to the top of the sand. You can't crack sand. And so below the top of the sand, we would still have seepage through the sand coming down the back of the wall here. And that would cause the water pressure to drop off with depth more rapidly than the hydrostatic pressure. But we would also have some active earth pressure there. So the loading diagram is somewhat different when we have sand beneath the marsh. Seepage analyses, we looked at 4 different cases that varied with the inland water level over at that Warrington Drive drain and our possible different heights of water in the canal at the time of failure. We did finite element analyses of those conditions, and it came up with 4 different possible uplift pressure distributions shown by these 4 dotted lines. The solid line down here, this is the total overburden pressure. Any water pressure higher than this would tend to lift the marsh up, and when that happened, of course, you're not going to get a simple upward movement of an intact layer of marsh. You're going to have the marsh rupture. And when the marsh ruptured, then water would begin to flow through that rupture. Exactly how that would happen, you can't say, but you can say that certainly did happen. And so water would be flowing upward out of a rupture in the marsh. What you see here are the results of finite element analyses with a rupture through the marsh. These are 0.5 foot head contours, and the fact that they're crowded so close together here means that there's a very high hydraulic gradient right at the base of the rupture. If we now do a normal stability analysis, taking into account the high water pressures in the sand here, this is sand. It has a high friction angle, but it also has these high water pressures in it. And we calculate a factor of safety of about 1.2 with a gap down the back of the wall to the top of the sand. We did 4 different analyses varying the canal water level and the inland water level, and for each of those, we calculated factors of safety for instability, that slope stability mechanism, and those were all above 1 by quite a margin. They varied from 1.2 to more than 1.5. Factors of safety against erosion, though, with those high hydraulic gradients at the base of the rupture in the peat, those were all less than 1. And so we believe here at the London Avenue South breach that the mechanism was more likely erosion and piping than simple instability due to high uplift pressures. At London Avenue Canal North, the situation was very similar. This layer of lacuston clay here doesn't play a critical role here. When we begin to get seepage down and through the sand, of course, the clay blocks that seepage just the same as the marsh. And again, we did 4 different analyses with 4 different conditions, 2 for the inland water level here and 2 for the canal water level at the time of failure. The sand was looser there and the friction angle lower. So the factors of safety against instability were smaller at London North than at London South. And the highest one was about 1, and the rest were below 1. And so these are the factors of safety for our 4 cases, factors of safety against instability, and these are the factors of safety against erosion and piping. And roughly speaking, they're about equal, and it's much harder to tell which might have been the more critical mechanism at London Avenue North. But in the end, it doesn't matter very much. There was the same kind of mess when it was all over. So in summary, I have just a few points here. Formation of a gap behind an eye wall in clay reduces the factor of safety against instability for the reasons that I've said. Because when a gap forms behind an eye wall in clay, the load on the wall increases. That water pressure is higher than the earth pressure before the gap formed. And the length of the slip surface decreases. So we don't have such a long slip surface to develop resistance. Formation of a gap behind an eye wall in sand reduces the factor of safety against instability and the factor of safety against erosion. Both things suffer. When a gap forms behind an eye wall in sand, the load on the wall increases, the length of the seepage path decreases so that the hydraulic gradients increase, and the length of the slip surface decreases so we can't provide as much shear resistance. Now, gaps do not always form behind eye walls as the water level rises against the wall. There are many situations, many examples where gaps did not form. But whether or not a gap forms depends on the earth pressure against the wall before the water rises and the stiffness of the soil. Both of these things are hard to predict. Rather than trying to predict whether or not a gap will form behind an eye wall as the water level rises, it should always be assumed for design that a gap will form, because this provides a more reliable basis for design. Thank you very much. There you are. Oh, thank you. Yep.
We do have time for some questions. If anybody has a question, please raise your hands high. The lights are very bright and it's difficult to see.
No questions.
Oh, there's a question.
Okay.
Sir.
If the sheet had been stronger and longer,
I suppose so. If we had strong enough sheeting, and we drove it to the center of the earth, it wouldn't have failed. Now that's a joke, of course, but that's the trend, and I think that it would be possible to drive the sheeting deep enough to prevent this kind of failure, even with a gap behind the wall. And with respect to that, I know that many of you have probably seen photos, at least, of the failed eye walls. None of them were bent. None of them failed in flexure. None of them were deformed permanently in flexure. And so it wasn't the bending in the eye walls, but it was, as you allude, if they had been longer and long enough. We didn't study how long that would need to be. If they had been long enough, this could have been forestalled.
yeah, it's a thing that the fact that you have a rigid wall tied to the sheet pile caused the gap to form more than if you had a sheet pile alone, because the rigid wall has to essentially move horizontally for the sheet pile to develop.
Yeah, yes. The question was if the sheet piles hadn't been so rigid, they might have interacted with the soil differently, and the failures would not have occurred. I kind of doubt that. I think that you could make the walls more flexible, or you could make them effectively not much stiffer than these, because they behaved as if they were practically rigid. It's the soil around the wall that allows the deformation and allows the gap to open up in the back of the wall. So I don't think that wall flexibility or stiffness would have a first-order effect on these things.
Any other questions? All right, well, thank you again, Dr.
Okay,
Duncan, for your excellent
thank you.
presentation.
Thank you.